we started something called DES. DES stands for Data Encryption Standard. Data Encryption Standard. This Data Encryption Standard, DES, okay, was developed, okay, it was developed in the year of 1977 by NIST, National Institute of Standard Technology, okay? In the year, DES, okay, DES was standardized in which year? In the year of 1979, okay? So in the year of 1799, DES was on the standard level for international, data encryption standard algorithm. This DES is what? Is old, okay? Is an old algorithm. Is old algorithm which still used, okay, in today's security. Okay, we are still using this DS in today's security. One more point to understand for this DS. Okay, this is like introduction or background behind it. This is like intro, okay? This is like the intro of DS, okay? What you have to know about DS, all right? And the important points to know about this DS, the main point to understand about this DS, the main points also to understand about this DS, it is this as follows. All right, so the DS, as you know, DS, okay, DS, which is the data encryption standard or data encryption algorithm. We call it data encryption algorithm, which stands for DD. Okay, sometimes the people call like this way. It has the following points, okay? Important things which compose this one, okay? D is made of what? D, data encryption standard, follows faster, okay, structure method, okay? It follows, it means it use the same steps, okay, method. Number two, to understand for this one in the data encryption standard, the given input, the input, hold on. So in this one, the input is of 64-bit block, okay? Second, the input key, the key is of 56-bit, okay? The input key, all right? The third point to understand about this DS, okay? DS passes, DS, okay? DS uses 16 rounds. Means, what does it mean? This means, what does it mean? Means that input, or into parentheses, plain text, okay, passes through what is going to pass through 16 rounds. 16 rounds, okay? This is the way. And we have seen also, we have confirmed that, in each each round, there is a subkey. A sub what? A subkey. All right. The size, next point, the size of each subkey is 48 bits. Clear? Every subkey has 48 bits. Okay. The total, okay, number of subkey is 16. Okay, 16 subkeys. 16. Okay, we have a 16 subkeys. All right. Next point to understand, which also is important about this DS is what? All right. The last point for this one, for this DS, is like the ciphertext CT is of the same size as a plaintext. Plaintext means what? Means ciphertext is 64-bit block. Okay, size. Ciphertext is equal to 64-bit block. All right, 64-bit blocks. All right. So now, as you can see, for these important points to understand in this DES, there are one more important which you have to note down. All right. What are the main component of DS? Okay. We are going to see what are the main component of DS. All right. I hope you have written. Let me erase this one. All right. All right. So these are very important algorithm which often being asked, okay, in exam. All right. Main component, I call them component of DS. Okay, what is making this DS? Okay, how is it being made? All right. Number one, for this main component of a DS, okay, DS is made by, number one, is made the so-called initial permutation. Initial permutation. That is number one. Number two means first the input, means the input key or the plaintext is going to pass to permutation, means changing from one side to another. That's shuffling. Let me call it like a shuffling. Okay. Number two, this main component, hold on. Yeah, the main component which this which makes our plaintext, which makes our DS is as follow. Okay, we have so-called the round key. Okay, we have so-called the rounds. Okay, the round key, no problem. Yeah, we can go round key. All right. And the second component which made this one is so-called not round key. This is a round function. Sorry, round function. The round function. And number three, we have the so-called key. Okay, key schedule or schedule. Number four, we have something which is called the final permutation. Final permutation. All right. So these are the four important points to understand in this ciphertext. I mean this not in this data encryption standard. Initial permutation, round function, key schedule, and the final permutation, okay, and the final permutation. All right. So I just want to show you how these things all happen in one diagram, okay, in one diagram, all right, or in a structure of DS. So what did I say? I say that we have something called plain text, okay, PT. This is a plain text. This plain text is of what? Is of 64-bit, okay. This 64-bit plain text, okay, we'll go to the so-called data encryption standard. This is what? This is going to be known as encryption mode. We want to encrypt the plain text. Okay, let me write as, yeah, we want to encrypt it, this one. Encryption. Okay, this is encryption. And when we encrypt this one, it has to do what? It has to give us a 64-bit ciphertext. And we have to use the key here. We have to use what? This is a key of what? A key of 56 bits. Okay, 56 bits, which means that the size of plain text, as you can see, is the same as the size of what? As the size of a cipher text. All right, as a size of cipher text. Now, how these things can be viewed, okay? What can be the view for all these things as we include initial, round, key schedule, and the final permutation? Look at this, okay? Look at this diagram here. For this, it's the simplest diagram in order to help you to understand how this plain text is going to be encrypted. Let me underline here. Here we have a 64-bit, okay, of plain text. Okay, this 64-bit plain text, as we have them here, this 64-bit plain text, they are going to do what? They are first going to pass to so-called initial permutation. Initial permutation. Initial permutation. Okay. This initial permutation, you will find this initial permutation abbreviated as IP. Okay, as IP, so that you can, you can understand when you read in some of the document. So this initial permutation is followed by round. We go to the round 1. Okay, we pass the round 1. We go down here, round 2, round 2, okay, and so on till we reach to the round number what? Round 16 here. Sorry, I'm supposed to write up here. I'm sorry. Apologize. Okay, let me erase this one. I hope you have written, since the table is a bit lengthy. So same, we continue from there. So we'll write it here. Okay, we started from plain text PT of 64 bits. 64-bit plain text of 64 bits, and this, it goes to the IP initial permutation. Is going to pass to initial permutation. This initial permutation is going to go to the rounds. We start the rounds. What a round? This is going to be round 1. It's going to be the round 1. This is going to be round 2. Round 2. Okay. How many rounds do we have here? We have 16 rounds, okay, till we reach to the 16th round, round 16. So once we reach to the round 16, this round 16 is going to pass to another stage called a swap. Okay, we are going to swap what? We are going to swap. Swap means that this is a faster structure start to happen here. Faster structure start to happen here. You remember, for faster structure, we have a 2 sides. For faster structure, if you remember, we have a 2 sides, 2 halves, left half and the right half. Plain text is divided into 2. You remember this one? When it is divided into 2, This one, it goes through a function. We pass through a function applied along with the key here. Here, the key is going to be applied. This is the key. And left side, we are going to use XOR function, XOR operation, sorry. And the output is going to swap to here. Means the left is going to be the right, and the right is going to be the left here. And here we are going to have what again? Right side here is going to be right side, is going to be left. We do the same. Down here, we are going to have a function. It's going to be applied along with the key. Sub key is coming here, key 1. And this is going to be applied to what? It's going to be applied to the second XOR operation. Okay, the output of this is going to be applied here. This is going to be swapped here. All right, it's going to be swapped here. So this operation of XOR, is going to happen in our DE. Okay, here to this place here. All right, so we have a swap. Okay, here we swap. This was a swap. This was a swap here. All right, so this swap, the swap is going to give us to the final permutation. This is what is happening internally, okay, inside your D. Okay, final permutation. Let me call FP. Final permutation, FP. All right, this FP is going to give us the last one, which is known as a ciphertext of 64-bit. Okay, ciphertext of 64 bits. All right, as you remember, for every round, we have to apply the subkeys. For every round, remember as initial, okay, as initial, we have something which is called, what is that? 56, okay, bits. This is a key. All right, we have a key. This is a key of 56 bits. For every round, we are going to apply the subkeys. For every round, we are going to apply what? Subkey. What is that subkey? Here we are going to have a 48 bit for key 1. Okay, for key 1. 48 bit for key 2. And this it goes on to say or to form until we find 48 bit, okay, key 16. Okay, key 16. So this is how it happens. Remember, these are the what? These are the 16 subkeys. Okay, 16 subkeys. We have to find 16 subkeys. All right, and when we come to swap here, for the swap, okay, for this swap, we mean that the input means the PT, plaintext, is divided into 2 halves. Okay, into 2 halves. What is that 2 halves? 64 divided by 2 is equal to 32 bits. Okay, left and side. So which means the left side and right side will be 32 and 32 for making that fiesta structure. Clear? Fiesta structure. So this is all about the component of DAS into diagram structure. All right. So let me share you, and we are going to go one by one, and we see what does it mean permutation, what does it mean round 1, what process is happening in round 1, and what process we have seen what is happening in a swap, and the final permutation. Final and the first permutation, they are all alike. How they are all alike? Because in this permutation, okay, without taking too much of the saying, look like here. All right, okay. For this first, we have like 1 bit, 1, 0. Okay, we can have like 0 again, can have like 1, like this is 1, and so on till 32 bits. Okay, because it's going to be like this. Let me take like 32 bits. Okay, so these bits, 1 is going to swap is going to come to the last. Okay, it's going to come to the last here, and this may come like to the first column. This is going to come like to the third column. I mean to the second position. This also goes like here. It's like this. So they swap. There's a swap, means it's going to swap from one position to another position. Okay, this is known as initial permutation. If your input bits was like 1001 100, so if you are going to swap, you may find the swap become like a 0 or like a 01 10 011, like that one. So it's going to swap in such a way. Okay, why? Because the security has to be attained within or inside the D. That's the main purpose. So if in case, if a plain text, okay, if a plain text falls in the hand of a crypt analyst, then he will be confused how the sequence of bits are. That's why we have the initial permutation, goes to the first round, then we apply the key here. This is like a Caesar cipher. No, is it a Caesar cipher? You remember the technique which you have seen, which is called transposition. Ready on fence, okay? The ready on fence, okay? Ready fence, which means keyless, okay? Keyless cipher. You can take the same as a keyless. There's no key applied to this one. Keys start to be applied to the round one. Now, number one, we start to do a transposition or a permutation here, which is known as confusion. Okay, confusion. Remember, I told you two things when we started the Fiesta structure: confusion and the fusion. Okay, and the fusion. So we start the confusion, and when we come to swap, we may have like a fusion. Okay, fusion. All right. So let's look. Let's see what does it hold. Okay, what does the notes tells us here? Anybody has a doubt or a question before I share you this? Okay, good. Okay, fine. So let me do this. Let me share you the note for today, and you will see what is there. Yeah, okay. This was about the, okay, data encryption, which is the first time we have seen all of this. Okay, let me go. These are the rounds. You can use the same diagram. You can use the same diagram, but for me, I have elaborated in this way. Okay, I have elaborated in this way. All right, if you use the same, no problem. But the main things to understand, as you can see to the diagram which we have here on PPT or on your PowerPoint presentation, where, hold on, I just want to bring a razor. Okay, as you can see here, we call it round key generation or generator. 56 cipher key, that was a 56 here. It was, you know, it was divided into sub keys, 48, 48, 48. Okay, same. All right. So, okay, these are the final initial key schedule around. All right, that's all. Okay, this is the so-called initial permutation. As you can see, initial permutation. As you can see, there is a swap. It was the first position. Okay, first position. It goes to the fourth until 64 bits. Remember, we have a 64 bits. All right. As you can see to the board here. For me, I gave you example of 32, right? Because there was no space. Let's take an example. If it's 64 bits, as you can see. Let's take an example. We have like this one. Let's take an example. We have 1, 0, and so on till another one. Let's say the final is 1. The first one occupy position 1 till it comes to position 64. So this is going to swap. We are going to have the swap. The 1 it may come here, and the 0 may come here. We may have a 0 here, may come have 1. The position is going to swap, as you can see here. That's the first initial permutation. All right. So, okay. So, what is the second one? That is the initial permutation. Same from the first to the last. As you can see to the table, once we finish the swap, then you're going to do the final permutation in order to have a strong ciphertext. All right. These are the key positions. 58 position. Okay. As you can see to this table for initial permutation, look, something, I forgot to mention this one, please. I forgot to mention this one. Can I erase this one? Let me erase the board here. Okay. There's something called the matrices are very, very important. Okay. In the class of network security, especially cryptography. Okay. Matrices are very, very important because by using matrices, we will be able to have the fusion. We will be able to have the fusion and confusion and co-fusion. This fusion and confusion, they will give us something which is called, permutation, and substitution. Okay, substitution, or it will give us something called or transposition. Okay, let's take these two, permutation and substitution. They will give these two. All right. For the data encryption standard, for DES is made of a square matrix of 8 by 8. Okay, is made of square matrix of 8 by 8. What does it mean? We have 8 rows and 8 columns. Example, we may have like 1 0 1 1 1 1 2 3 4 5 6 7. Okay, 6 1 2 3 4 5 6 7 and 8. Okay, and we may have another 0 1 0 0 1 1 0 1. Okay, till we goes to the 8 1 1 2 3 3, we goes to the 8. Let's say this is the 8 1. Okay, 1 1 1 0 1 1 0 0. This is the 8 1. Okay, this is a matrix. We have the matrix 8 by 8. So as you can see here is a position 1. From position 1, 2, 3, 4, 5, 6, 7, 8. So here 1, 2, till you go down. Here is 1, sorry. 1 row, the first row, second row, till you go to the 8th row. So that's why we have a 64 bits. Okay, 64 bits. So they will be arranged in a form of matrices. Clear? That is why instead of writing the bits, as you can see to the table here, we write the position. Position number 58, okay, followed by 50, like, and so on and so on. As you can see, does not exceed 64. Okay, does not exceed 64 position. It goes to 63, as you can see there. Okay, the highest is 63. If the highest is 63 means what? Means we start from position 0, because we start from 0. We start from the position has to be n minus 1. Okay, the position I can say n minus 1. Okay, similar case if it was 63, it also have to have 63 position starting from 0, because 0 position counts in array, in array formulation. All right. So as you can see see the 58 bits of input X will be the first bits the same. This is called permutation. Okay. All right. So this is all about it. Now this is the round function. Okay. This is the round function. This is the round function which happen for every round. Okay. For in each round you are going to have the first structure. I will show you to the next slide. Yeah. What happened for every single round. This is very, very, very important. Okay. This is very important. What happens for every round. Very important. Okay, to understand what happens for every round. All right. Look here. Here is a single round DS. Okay, DA, data encryption standard, single round. Remember, we have how many rounds? We have 16 rounds. we have 16 rounds. Okay, for this single round, for single round, as you can see, when we come to the single round, the input means 64 bits of plain text, okay, is divided into two halves. Divided into two halves, okay, which means they're going to be 32 bits each. Okay, 32 bits each. All right. So these 32 bits each, 32 bit each, they are going to do what? These 32 bit each, they're going to be passed to so-called XOR, okay, operation. Okay. In this XOR operation, we are going to apply a sub key. We are going to put a sub key, okay, of 48 bits. 48 bits. All right. So this XOR, it will give us the output of 48 bits. 48 bits. They're going to be increased. So these 48 bits, they are going to pass to so-called, you know, S box. 8 S box. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6. Okay. 7, 8. S1, S2, S3, S4, S5, S6, S7, and S8. As you can see, they pass through this S box. So this S box, every each, here I can say each S box, okay? Each S box contains or store, let me say store, each S box store 6 bits. Okay, means here we're going to have a 6 bits, 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 and the total will be 48 bits. All right. Once this 48 bits, once each box contains 80 bits, 6 bits. Once this stage is over, what is going to happen? We go to the final permutation. The final permutation, or this is a final permutation, which is known as it's a final permutation. Let me call it final permutation. The final permutation is going to give the output of 32 bits. 32 bits. All right, for the final permutation. So this is the thing which is happening for every round. 32-bit input, when they pass to XOR, they are going to be increased. You remember how is it increasing for this one? How it increases, all right? For data communication network, you remember the so-called the parity bits. How to calculate the parity bits, okay? If you want to calculate the parity bits, if you have like 1, 1, 0, 1, 1, 1, 1, 1, 2, 3, 4, 5, 6, 7, 8. Let me give like this one, 8, okay? And in this 8, let me give, yeah, is 32. Let me have 8 for 4 bits, okay? Let me have 1, 0, 1, 1, 0, 0, 0, 1. Let me give like this one. This will be 0 for XOR. 1, 1 means when both are true, when both are 1, they become 0. And 1 is going to be carried up here. It's going to be 0. 1 is going to be carried up here. We're going to have a triple 1. Triple 1, we're going to have a 1. And 1 is going to be carried. 1, 1 carried, 0, 1, 1, 1. And here we're going to have what? It's supposed to be 0, right? It's supposed to be 10 like this one. Okay, if it's supposed to be 10 like this one, this comes here. So it keeps increasing until you're going to have 8 bits. Same thing will be applied. All right. So this is the 2 bits. This one you will see. You will read it, and this is the detail how it goes from one to another. Internal detail. Okay, internal, how it happens. All right. How does it happen for internal? This is important to know how these things works. I repeat, you have to know how to design this single detail, because it's a very important points in DS. All right. As you can see, the input. Okay. As you can see to that diagram which we have there, Still same thing is being applied, just for you to understand, to distinguish or to make it easy for you. Same thing, same single round, okay? Details for single round. Now we had a plain text or input of 64, correct? 64 is going to be divided into two halves, okay? Because it's going to follow first structure, two halves. What are those two halves? The first half is going to be left I1 and right I1. This is going to be 32 bits. This is going to be 32 bits as well. Okay, 32 bits as well. Same thing is going to happen also to the key. The key was, what was the size of key? The key size was 56, okay, bit key. Okay, this was a key. All right, so the key as well is going to be divided into two halves. Okay, one is going to be left, another is going to be right. It's going to be 28, it's going to be 28. All right, so this is going to be the left side. As I mentioned, left side is going to be the right side. All right, as you remember, for the right side, for the first right side, okay, for the first right side, we are going to do what? We are going to have one permutation. Is going to go, remember the input, the first step, input goes to the permutation. You remember the permutation, changing, swapping the position, is going to go to so-called expanded permutation, or expanded, it can be expanded or permutation, or a permutation. Okay, it can be expanded or permutation. That is number one. Number two, this one is going to give us 48-bit when it expanded. When we put like this slash or this forward slash, or backward, this backward slash, what do we mean? We mean the input, the output. Okay, this is what's going to be the input, or what the key have you entered. If I do this, and this is going to be 48. Okay, if I do this, this is going to be 28. Okay, I may do like this one. Okay, to mention what a key is going to be applied in this one. Okay, if I take like a half, of the bits. All right, if I take the complete bits for 56, then I'll make 40. No, for single round, you remember, for every single round, you're going to use 48 bits. Okay, 48 bits. So same here. And then the output which we get is going to go to S box. S box. All right, for substitution box. How many boxes are here? We have 8. 8 boxes. Each box has 6 bits. Okay, 6 bits. And the final one is this going to go also to XOR function. XOR function. As you can see, we are going to swap. This XOR function is going to be swapped to this one. Means this is the function which we are performing here. Okay, there's a first function which performed, and then we go on and so on, as you can see to the diagram here. And then the key has to be applied here. Okay, the key has to be applied here. Here we can have XOR. Okay, here we can have XOR. Here we have XOR here, and the key is going to be applied here. Okay, 48 bit. Okay, 48 bits. All right, so and so on, as you can see. So just important point to understand for this one is to know that the bits going to be divided into two, and it's going to be expanded. And when we want to form the ciphertext, okay, the ciphertext will be the same size as the input which you have entered. All right, so all these things. Now, these are the advantage of the DES, data encryption standard. This comes under 2 marks or in interview. What does it mean? Average effect of DS. This one, average or avalanche, it depends by how you pronounce it. It says that a small change in a plain text result in a very great change in a ciphertext. Means if you make a minor, take an example for this permutation, when you do the permutation or expansion here, if you make it was 1, is obvious it was 1 0 1 1, but for you make 1 1 0 1 1 completely. It does what? Okay, if it was like this and like this, and it came to happen that you make like this one. All right, so this it makes a very great change. Very great change. This is known as average effect. In order to make what? To make a ciphertext very strong. What does it mean, average effect? A small change in a plain text, okay, is going to give is going to result in a very great change in the ciphertext. Any change you made in a plain text is going to give a very bad reflection in a ciphertext. What does it mean, completeness? Completeness means each bit of ciphertext depends on many bits of plain text. Okay. So this is also all about this. Anybody has a doubt? Anybody has a doubt? I think, yeah. Anyone has a doubt? All right. So if there is no doubt, thank you for joining today's class. Let me